Okay, so now that we understand vectors a little bit, what we're going to do is we're going to talk about, we're going to kind of take a half a step back, and we're going to talk about distance, velocity, acceleration, and we're going to talk about plotting them on a graph. Because again, when we think about vectors, we're thinking about distance. The vector for distance is displacement, and the vector for speed is velocity. And we can use that vector work later to sort of define the addition and subtractions of speeds or velocities, excuse me, and displacements. But what I want to get back to here is I want to talk about what displacement is on a graph, and what velocity is relative to displacement, and what acceleration is relative to velocity. And I'll look at the graphs of all of these. So let's start with an x. Oops, let me get a black marker here. Let's start with an x. Let's start with just a simple x graph. Okay. If I end up starting at a position here is 0, let's call it 0 meters, because that's where we're at. And let's say you're right here. Oops, let me draw that again. And you're kind of stepping back and going forward. So you are racing along the line, okay? And you're at the 0 mark. You're trying to get down to, let's say, 10 meters. And so as you move along, you are ostensibly going ahead and you're trotting along, down to the 10-meter mark, right? Well, that's our displacement, right? It's just, we want 10 meters away from the initial 0 meter. When I think about it, when we think about it in terms of two people, all right, and let's have, let me get rid of this and go into a different layer. And we're going to have him here, okay, and this is racer A, okay, and I'm going to have, racer B, okay, and he's going to be here. Oops. Paste. There you. Here's my racer B. Okay. And again, we're trying to get from the first point to the second point. Okay. So my two racers are here, and ultimately we're going to get this guy to go from the 0 mark here over to the 10-meter mark. And they're both going to get there, right? They're both eventually going to get to that point. Oops. But the issue is we need to know who's going to win. We need to understand that there's a time issue, right? So if over a certain amount of time, that if my racer A is going faster than racer B, okay, then at the end of the day, I want to make sure I know who's winning and who's not. Come back here for a second. Okay, so we want to make sure that and we think about displacement, and we think about winning and not winning, so to speak. What we're really worrying about is we're worrying about how these guys are doing relative to time. So that's the big issue. So we're going to change. We're going to go 10 meters. So really, if we look at this, we have our position of x initial, and we have our position of x final. Okay, that's an F and that's an I. Okay, so x initial and x final, and our delta x. Okay, erase that again. Our delta x is equal to our x final minus our x initial. This is very important. And then what's important about this, guys, what's important about this is that we look at this idea that it's final minus initial. So if I think about this, and I look at put the map, delta x is equal to 10 meters minus 0 meters, which gives me a change of positive 10 meters. And the reason why I'm harping on this is that if we think about our guy starting here, and maybe in actuality, maybe he actually starts here and goes this direction. If he starts here and goes this direction, initially at 10 meters and ends up at 0, then it would be delta x equals 0 meters minus 10 meters, equaling negative 10 meters. But the difference between this depends on our x final being, knowing what the x final versus our x initial is, right? If we're starting at 0 and going to 10, and that's our final position, then 10 minus 0 is a positive 10. And if we start at 10 and go to 0, then we're going backwards, being a negative 10. This is very important. We gotta not lose sight of that, because that sign is really important. So we think about our position.
At this time.
The big issue now is that we go back to this whole time issue. Well, we're all going to get to 10 meters. We're all going to change a distance, have a change of displacement of positive 10 meters. But what we need to know is we need to know how fast we did it, because we want to know who's better, A or B, who's faster, A or B. So we look at this delta x, okay, which is our x final minus our x initial. But it really depends on the time it takes, right? And let's assume that it takes a certain amount of time. Let's say it takes 5 seconds. And we're going to say, so that means we have we have 10 meters that we went, a positive 10 meters, over a positive 5 seconds. So that means we've gone, 10 divided by 5 is 2 meters per second. That was our speed, okay? That was our speed, or in given a direction with a positive. If it's positive, then we can say it's a velocity, because we know it's positive in the x direction. But this time issue, this guy right here, it's not just a flat time, it still is. So giving it over time, that means that it's really not just time, it is delta x over delta t, where it's really 5 seconds minus 0 seconds, where it actually, I'm going to erase this for a second and rewrite this, right? I'm going to rewrite this up here. We're going to say it's time final minus time initial. So it's 10 meters minus 0 meters over 5 seconds minus 0 seconds. I arbitrarily picked 5 seconds. Let's say it takes 5 seconds to get there. And that means you have a velocity of positive 2 meters a second. So that means you're moving 2 meters a second, in the right direction, because the right is positive. Okay. So let's assume that that is for option B. Okay. And let's say option A, he's doing the same way. So let's say he's delta x, right? And it's going to be delta x of B and delta time of B. So delta x of A over delta time of A. Okay. That's going to equal, now look, they're going to the same finish line. We're still going 10 meters. So the final distance is still 10 meters minus 0 meters. But let's say runner A gets there, not in 5 seconds, but let's say he gets there in 2 seconds. So he's going to get 2 seconds is, let me come back for a second, our time final minus our time initial. Okay? And I'm actually going to go back here. So again, it's x final minus x initial, and again, it's going to be 10 meters minus 0 meters. But this time, our final time is going to take us 2 seconds minus our initial time of starting at 0, because we're all going to start at the 0 point, right? And that's going to equal 10 divided by 2, which is positive 5 meters per second. So we know that runner A is going faster than runner B. And this is really important. I know you're saying, well, yeah, Mr. A, this is really simple, I get it, but I want you to really pay attention to this final and this initial thing. It's always the delta anything is always the anything final minus the anything initial. Remember that. That's important, because that piece, and again, that piece is going to determine our sign. You know, are we going to the right? Are we going to the left? Are we going positive? Are we going negative? Okay, so keep that in mind. And again, we're looking at this and we're saying our change in distance over our change in time, that is our velocity. Okay, so what I want to do is I want to kind of table this for a second and kind of look at this on a position versus time graph. So we originally looked at this. We looked at the graph at our position, and we kind of talked about time. But let's do this in a two-dimensional graph. Okay, so if I look at this in a two-dimensional graph, we're going to put our position here, and here's our time. And typically, guys, you put time on the x-axis, and whatever else it is, we're going to put up here. So we're going to put our position x. Okay, so if we started, and we're going to replot what we have. We're going to replot. I'm going to come back here first. I'm going to grab this guy. I'm going to plot. I'm going to do this guy here. All right. Copy. Come over to here. I'm going to paste this guy. So here's this guy. We're going to shrink him down a little bit so we can see him. He's there. We kind of know that. Let's see. Is that right? Yeah, we're going to take this guy. We're going to get one of these guys here. Copy, put this back up here, paste, and we're going to shrink him down a little bit and put him up on top of here, okay? So we're still dealing with the exact same scenario, but what we're doing is we're plotting him on a two-axis graph versus a one-axis. The original one was a one x-axis, right? But now I've done is I flopped it, so I've said vertical is my x, my position, over time. Because anytime we deal with time, time is, by standard, on the x-axis. So what's our initial time? Well, initial time is going to be 0, right? So our initial, I'm going to go ahead and start applying this in a different color. Our initial time is 0 seconds, right? Oh, and what's our initial position? Well, our initial position is 0 meters, okay? And what is our final? This is going to be x initial, okay, and this is going to be time initial, right? And let's say our final position, our x final, is 10 meters, right? And we know that, so that's going to be out here somewhere, up at the very top, somewhere along this line. And let's say our final time is going to be, let's call it 5 seconds. That's our final time. Oops, excuse me. Our time final. So I can plot that point, and here's a point. And anytime I've got 2 points, then I can take and I can draw a line between them. And you'll notice that this line is straight, okay? That means that what this straight line implies is that my velocity, okay, is the same no matter where I am on the time scale. That's what this implies. Now, it may not be the case. Maybe in the first second he walks for a little bit, and then at time 2 he runs. We'll deal with that in a second. But let's assume that he starts at the time 0, the gun goes off, he travels at the exact same speed from the beginning to the end. So at any point in time, we are traveling the same speed. And what is that speed? The speed is, again, our delta x over our delta t. And again, that's our x final minus our x initial over our time final minus our time initial. Okay, which is equal to, move this stuff out of the way, which is equal to our x final. What's our x final? 10 meters minus our initial distance, which is 0 meters, over our final time, which is 5 seconds, minus 0 seconds. So we end up with this delta x over delta t, which is really our velocity, okay? And I'm going to put an arrow over it just because we're going to talk a little bit. I'm going to make sure we're talking vectors here for a little bit. So vector velocity is equal to 10 minus 0, which is 10 meters over 5 seconds, which is equal to 2 meters per second, positive. And that's our velocity. Now, if anyone remembers this from geometry, what does this represent, this delta x over delta t? Well, that, if anyone remembers, is our slope. Remember y equals mx plus, oops, excuse me, mx plus b, right? Where this is really our y, even though it's saying our x, okay? In this case, it's x equals m times our t plus B, where this is the y-intercept. And in this case, what's our y-intercept? Well, where does the curve intersect our y-axis? I know this is an x, but it's or the x-axis. Well, that's going to be, it's really 0, right? And so our slope, this guy right here, is our slope. It's the delta x over delta t. So at any point in time, we can figure out what our position is. So we can say that, okay, what if I want to say what if I want to figure out where am I, what position am I on at, let's say at 4 seconds. How do I figure out what position I'm at 4 seconds? Well, that's how we figure this out. X equals our slope, okay, which is m times time plus b, which is equal to our slope, which is 2 meters a second, times our time, which is 4 seconds, okay, plus our initial position, right, because our initial position was 0, and that's what the y-intercept really means, our initial position, 0 meters. And so x equals 2 times 4, which is 8. And notice, now here's the big thing, right? It's meters per second times second, which really means that it's 2 meters per second times 4 seconds over 1. So we can cancel our seconds and we're left with meters. So it really means 8 meters. So at this point in time, we should be at 8 meters. And this is the power of this graphing, is that we're going to be able to figure out at any point in time where we are. And this is now your geometry and your algebra being applied to sort of this physics concept. So you can now figure out where we are at any point in time.